Hello, everybody. Thank you very much for joining today for this discussion on functional composable operations with Unix-style pipes in C++. You would think, how would Unix-style pipes, how can they be applicable to C++? But as we all know, the C++ world is going more and more. In fact, not only C++, almost all languages are going more and more functional these days. And when it comes to functional, it's all about composing operations, pure functions, lack of state, working with values, and what better way of dealing with it than pipeline as a mechanism. So today we'll explore how we can make sure we can write just like we write Unix commands, piping into each other, and they just work. We'll see how we can do the same with C++. It becomes totally declarative, and the what is happening in the code is totally apparent when you look at that code. I've just, this is the session from 1 hour ago. I hope many of you were there for that one where Victor talked about pipelines. And I took the opportunity to take a screenshot. I have not taken his permission, but I think I'll apologize later. So we have him quoting Doug McClory that, you know, it's so easy to do so many things in Unix shell script. And the pipelines is all what it is about. So when you work on your C++ code, you would see code like this, which is composed of many steps and operations one after the other, or something like this, where you are dealing with many algorithms and managing state and temporary, the objects and their state, basically. You could have a little more disciplined code, something like this, where you use the modern techniques of Std Optional or whatever. In all the cases, nothing beats the expressivity and the clarity and the declarativeness of the pipelines. When you see a Unix pipeline, something like this, you know that from the left, it's doing a sort, then unique, sort, head, and you know exactly what's happening. It's just works like a charm. C++23, like this on your screen, is going to come up with a Monadic interface for Std Optional, which really helps you do almost what the Unix command line says. But I don't like that. I would love to have something like this. Truly, piped operations into each other. So let's see how we can make this happen. I'm Ankur. I'm an architect at Expo. It's a telecommunication product company. And I'm a polyglot when it comes to natural languages, but C++ stands to be #1 for me. I'm very active in the CPP India, in India community, and cherish working on high performance products and cloud native products. So, functional composable operations. Ways to realize, we look at this today. So this is the agenda for today. We look at how to realize chained operations, truly chained operations. We want to be generic and expandable so that you can use it in any context. It doesn't have to be bound to something like ranges, for example. And we look at some considerations like customization, resource management, etc. We look at C++17, which brings in Std Optional. Then we look at how to use C++20 concepts and how not to interfere with the ranges, because if you, as you would guess, spoiler alert, the pipe operator, the bitwise OR operator is the pipe operator. So when we overload it, there is a chance that we interfere with ranges, and how to not get there. And then finally, improving on the future. You know, hindsight is 20/20, but what about future? Can you improve the future that is going to come? Well, I just attempted that, a small little attempt there. So we are looking at flexible and clean ways of code without visible clutter. How great would it be that you are able to see your business objects and business operations right there, rather than a lot of syntax and ifs and jumps and checks. it's just, it would be a perfect world, I would say. The code that I'm going to share today during this presentation is present at this location on my GitHub under the repo called as generic pipeline. And you can follow along if you go there. The session, like I discussed, is in 3 or 4 parts. First one going through C++11, and we would be able to achieve all of that through in this session in C++11. And then we go on to other. So you can see the folders here are named as C++11, C++17, 20, and 23. Okay. So just a quick look at Unix. I think all of us know how they work, and that was the image that we saw previously. Sort colors and count unique items there. Then sort in reverse order and take the first 3. This will exactly give you your favorite 3, which is the most occurrent colors in that file. You don't need much to understand this. And if we look at some real practical other examples, this is just an example which I got online, that image. But something that I can say we do day in, day out is take all the compilation log, look for all warnings, look for, manipulate the string into something else, suppress all the text which is prepended and leave only the errors, and have a list of all the unique errors that you want to address in this release. Lovely. If you have a build broken, you can do a git command, pipe and cut, and pick the mail and just send an email to somebody. All those who have committed something yesterday. So if we look at just the same problem, I won't spend much time. Victor also talked about this in the last hour. If you try to achieve the same thing with algorithms, it would be time consuming, and more than that, too verbose. I wasn't happy writing this, but I had to do it to show it to you, the contrast. The algorithms do not compose well, and many intermediate steps. And we know there is a solution for this. It's ranges, and we'll just take a look at it. So let's move on to considering ranges. You see, we have a vector here of some numbers, and if we conditionally copy these, only those which are divisible by 3, and then square them, you would get the output that is the intended program here, get the squares of numbers divisible by 3. And if you see the same thing with ranges, this is from, again, the same Microsoft site, just an example that I just took from their site. It would be so straightforward like this. For all the input, filter those that are divisible by 3 and square them. It can't get clearer than this, or maybe, but not for ranges for sure. Ranges are impressively clean and straightforward, extendable. They convey the intent right there, and they are efficient. Of course, they are lazy, and they really work wonders with the pipeline. So I'm all impressed. I want to use the pipeline everywhere. I'm just like almost hypnotized. And everywhere I see an opportunity to be able to do this. If you consider a messaging system, X sends a message in group Y, let's say it's your WhatsApp, it would go through a series of steps of receiving a message, finding who you are, that you're authenticated, finding which group you are sending, are you a part of that group, and then make sure the message reaches to the other side. If you take something in an IoT domain where there's a constant push of events from many devices. Events originate at devices, they land on some server, they have to be enriched. You have to maintain some kind of a history, and you might want to refresh some views at the end of it. It all is so sequential and step-by-step operations, one after the other. Of course, perfect candidate for pipeline. But we are talking not ranges, but single messages and business context and domain objects here. Really? So when you're not working with ranges, would we be able to work on, with a pipeline? And of course, the answer from me is yes, and why not? Let's make it happen. Let's just consider a simple scenario of a queue connect. This is a real example from a project that I have seen, and we were using a library called as librd Kafka, which has many steps to start becoming a consumer. Kafka, if you know, is a queuing system or a messaging system where you can register and consume certain contexts of messages based on a context. So the step that you go through in order to work with the Kafka, becoming a Kafka consumer when you want to get the messages from Kafka, it would be something like this. You read the environment variable, you open that config file. With that config, you have to parse it out into a configuration object. You create the Kafka consumer, the real consumer, and then let it connect to the as per the configuration to the Kafka server. And now you subscribe to a topic. Topic is a concern, is the messages that you are interested in, and then you'll start receiving those. And what would an initialization look like? This is what we start with. And I have cleaned it up quite a bit to make it pretty straightforward and simple, even to start with. So you read the environment for this variable, you get the file name. If you didn't, you have an environment error. Then you read the file contents, and if you didn't get the file or something wrong happened, you don't have the contents, you throw an exception. You parse the config out of the JSON that you just read from the file. If that didn't work, an exception. And you have to keep on checking, because this is a return-based, implementation where the status is returned along with the object. The object is returned, and some of these states of the object, for example, the string being empty, is flagged as an error or as a problem. The contents being empty is an issue. Okay, and so. You see that there is all this interleaved error handling and checking. What do we really want? This is our destination. We want a Kafka consumer to be created. Okay, I've just stripped it out to make to show only the relevant stuff. Okay, it has these members of connect and subscribe. We'll come to that. And what is the path to reaching them? As you see, it is through all these steps. Okay, and 2 of these are member functions. Otherwise, they are freestanding functions. And the desired code is like this, just piped function names. Very impressive, I would say. And this is C++11, I forgot to mention. So on the slides on the top right, you see the C++ version mentioned. It's applicable for all the slides that have code. Okay, so let's start. We have a function called as getFileContents, and then in order to have the pipeline and invoke this function on the other side of the pipeline, we need to have a string coming through, which is the passed parameter, and the callable, which is this function itself. Okay, as you see, I've defined callable as a function which takes a string and returns a string. And that callable can be the right-hand side of the operator, and the left-hand side is, of course, the string. And there you go, you can just call the function with the value. This is C++11 code. And of course, I've used a trailing return type here, which is std string also, because your file is a text file. Now, this helps you write a code like this. You get from the environment and you pipe it into getFileContents. Of course, you get all the contents. If not, you can check and throw. Okay. Now, in C++, not everything is a function. C++ has many different kinds of callables, objects which have the function overload implemented, or you could have some lambdas or anything. So with those many options, you definitely want some generic code. You don't want to write a pipeline operator for every possibility. Of course, we are in C++. So we change the string to a T, and the callable becomes a templated parameter. So whatever the user passes, it needs to be it will be a callable which will get the value here, which is of type T. And that's the body. You forward the caller as is, and you forward the value also, and make sure that the operation happens. Whatever is the result is the return type of this operator. Okay. No surprises here. This is just a generic implementation of the same. But with that, you can definitely write this. And in fact, even the next operator is now added to the sequence here. So you get from the environment, not only get the file contents, but based on the contents, you also parse the Kafka. Now you can check this object, which is at the end of 3 operations, and you can get the same functionality. Beware, type conversion with templates is not possible. Like I tried to pass, pass this const-char string of 22, whatever number of characters, but I was taking a std string, and that wouldn't work because conversion is not allowed with template parameters. You may be knowing we are in CppCon. But so you have to make sure that the callable definitely receives exactly the parameter that it expects, being generic and template. Otherwise, the overload will not be caught. All right. Next, so we have member functions. These may be called too. So what do we do? If you want to chain operations, you could create free functions, which take the object instead of calling a member function on the object. Okay, if that's not possible, you could always write a custom function or a lambda, which does this for you. And if you remember from last time, from the desired code, the last 2 operations were on member functions. Once you have the Kafka consumer, you are calling connect and subscribe. Here we see a third type of a third method used in order to resolve to achieve the subscribe operation, and that's by encapsulating the member into this memfunc. Okay, use a standard library. You've got it. Just you have to make sure that the return type of member function is the same as what the next step in the chain expects. If that's not the case, you will have to wrap it up yourself or something. All right. So if you noticed, we are not checking the return types now. We don't know that the environment failed or parsing failed or the file was not found. We don't know. Let's see. So when create Kafka, which is the 4th function which gets the Kafka config, when that gets the object, it could check that the object is there and raise the JSON error exception. Okay. Or else it would just instantiate the Kafka consumer and you'll have it. Okay. Similarly, if we look at the next function, connect takes a consumer. If the consumer is not there, you know that the creation has failed and you can throw a creation error. So, and then if not, you can do a connect. But this is exactly what not to do. Here you have baked in the JSON error in the create Kafka consumer. There is an assumption in the implementation here that the previous step was a file parsing step. And here the assumption is the creation was a predecessor of the connect function. This is not what we want, of course. It's not far from imagination that you should raise the error exactly where you found it. If you're able to deal with it, then do it, or else you should raise the error there, not let it pass silently. So parse Kafka config. Needs to change. So you don't want to do what is being done in the first example. Okay, sorry. This is the parse Kafka config, and that's where you actually came across a JSON error when you actually started to parse it. And that's where you raise the JSON error. Sorry, I was reading this wrong. Then when you come to create Kafka config, as you see, this is just a straightforward function which takes something and does its job. It doesn't have to do any wrapping, unwrapping, checking. This is perfect. And when you come to connect, you try the connect. If you don't, if you're not able to connect, you throw the error right there. Okay, so now we have reached a stage that all of our operations are now piped through. You see, the init Kafka is equivalent to how we started with the code with all the checks, which was not so functional. This is functional and declarative, and you can exactly see what your code is doing. You ought to name your functions absolutely correctly. Otherwise, it'll be confusing, which is the case anyhow. So we've almost got our C++11 function working. Okay. Now, what are the variations that could be possible? Just to cover the landscape fully. If you try to move the operator to a generic namespace, I did that. I didn't like to add to the global namespace this operator, but it's not possible. When you do that, the operator becomes invisible to is not visible in context other than that that namespace. So I had to go back to making the operator global. You just no operator matches outside that namespace. Okay, now calling function templates, you could have some functions which are just not function pointers, they are function templates. For example, like this, you could have some configuration types of JSON, XML, YAML, and you would like to support all of these, but you want the format as a template parameter. It cannot be deduced by looking at the past parameters. So what do? Well, all is not lost. As you see here, the parse Kafka config is right there with the templated with the templated argument specified. So with that parameter, the template becomes a real function, and now the function is callable from this point, even if it was not instantiated so far. Okay, so we move ahead on the chain. Functions taking multiple arguments. You could have some of these steps taking many arguments. For example, I changed connect temporarily here to take not only on a consumer, but also it needs a certificate, because when it connects, it needs to do some secure connection. It's the reality. So you need that other parameter. What could you do? Well, if you just add that the additional argument and try to compile, you would definitely be flagged as the operator mismatch, because there is no function which matches, which can take one argument, which is what you're passing from the left-hand side of the function. Okay, so we bring our lambdas. Our friend lambda has come here. We make sure that the certificate is created before we get into the call. That's a little unfortunate that we have to do this here before entering the pipeline. Maybe we never reach there, but you would implement for the success case and try to optimize the success case anyway. You can even call that function here and directly pass the lambda into the connect function. But as you see here, it is captured. I tried to do that, do it the C++14 way, forgetting that C++11 doesn't support this. But just as a reminder, you cannot call the function and capture its value in the lambda capture. All right. So function taking multiple arguments. You could also use Std Bind. As you see here, Std Bind takes the connect function, says that the first placeholder is where you pass the past, where you place the past argument, and get certificate is what you bind to as the second argument. That's good enough. Works very well. You could have higher order functions. They combine many lower order functions, but they achieve with their glue, being a glue, they achieve larger operations using smaller ones. And you could basically get a new callable by passing some callable to a higher order function. Okay, we have more of these, many of these in the functional header in the Std. Now, if you consider this case, it's a slightly different case that a message has come and you want to process it. And okay, and there are two callables that it wants to mash up and create a third callable. I guess this is the way to do it. I have ended up implementing it here, which takes the two callables. So these two functions can be changed by anybody, by the caller, and they will be used as it is by this higher order function. Okay, so basically, if you have your pure functions and you depend only on the arguments, have no side effects or maintain state, you just either return or throw. That's the sweet spot to be in. Work with values and work with ownership. So many times these objects won't even get instantiated or placed in RAM memory. They would just be passed along in registers, perhaps. And it's a very optimal way of working. Return a new object created by the original object passed. Say you serialize, and composability. The example here I tried to give, I think this is a stale example from when I didn't change the slides. So this here, it is trying. All I'm trying to tell you is the new object or the original object, when it is passed, you get something else on the other side, and that's what you keep on working, and your chain continues. So you have to make sure that composability is achieved by every step getting, or every step processing what the previous step gave, and you transforming one thing into the other. For example, if you want to send something, the message is received, and you serialize it into bytes, which you can actually send it on the wire, on the network, for example. So this is a way of working on object. You just take the object by value and work on it. All right. So I see no questions. Feel free to add any. Now, errors and cleanup. Of course, we are in functional land. So, but is memory leak for dynamically allocated instances when they are passed around? Is memory leak possible? Of course, yes. And we have easy solution from 11 years ago, from C++11, to use the smart pointer, the unique pointer. And as you see here, this connect is working on a unique pointer of consumer. It's taking it's taking the consumer and giving back the consumer and just adding the little operation in the middle. And here, even if it gets into an exception case, due to the unique pointer, as you all know, the cleanup is assured. Either you return and you pass on the ownership, or you exit by exception and you still clean up. Okay. And in case you want to catch these exceptions, you don't want to let it trickle further. Of course, you can catch the relevant types and let the others, which you can't handle here, you can let the others pass through. Okay. So what if the first parameter of our pipeline can also be passed as an object directly? So if you remember, in all the screens that we had so far, on all the slides, the getEnv was being called by passing this. But here, even the string is being passed by piping it into the getEnv function. The std ranges do this, and this is possible with the same implementation that we have. It's just a T. Where it came from did not change anything. Okay, I tried to use the literals here. It won't work with C++11. So this is definitely possible, but is this something that I would recommend? It's a matter of taste. If you like it, you can use it. But having implemented the operator in that fashion, I guess still just allows for this to happen. So pipes are everywhere. Like I said previously, we can have some messaging system or a store system, like this is an event log, let's say. You receive a message, you parse it, validate it, extract the relevant information and store it. You could have receive message, valid, extract, enrich, and send. Now you're not storing, you are enriching with some more information and sending to another system. It's like a relay or a networking between devices or something. And you see those steps composed with new steps absolutely easily. If you take a typical web scenario, you would receive an HTTP request, you'll extract the body, which is where the interesting data is. You validate that it is okay, your JSON is all right, and you can actionize based on the request that the user has given, based on this data which you extracted. You make a response, the action gives you a response, which you send to the other side as a response, as an HTTP response again. You could have something which is not, which is internal. Maybe there is a trigger, okay, and you should publish a message every n seconds or something, and so you get a trigger, and again you would follow similar steps. If you make your code composable like this, where every functionality is a very small reusable piece, and you're able to mash different operations together, you can achieve many combinations in this fashion. And that's why the pipeline is such a powerful concept. Okay. So that was the C++11 part. If you look at C++17, what we got with it was Std Optional. Std Optional is a value type, and it wraps some value and carries it, which could be optional because sometimes you may not have the value. That's exactly what it is. Okay, I described what I have written on the slide here. So in our case, it can signal, it is actually the lack of an object. In our case, it can signal that a step has failed. And it's good enough for us to stop the chain and not go further. So if we take the example and use the optional with our implementations, create Kafka consumer, which previously we have even for a scenario discussed that it could be a unique pointer, which is dynamically allocated and passed around with ownership, etc. You don't even need that with Std Optional. You have Std Optional, which may or may not carry the Kafka consumer, and there it is your functionality of your possibility of failing or carrying the object where you actually have the object itself. Okay, and so the function is the same. Now all we are doing is wrapping it in an optional, and the return type becomes the optional. Okay. So no need to use your unique pointer. Yes, you can stay with values. Here, now you can check the optional. Of course, like functional programmers would tell you, do not open and check, or do the next operation on that. Whether it's an error, then you end up doing an error operation. If it's a successful object, then you can start using it. Right. So we have the use like this here, which so cons is actually an Std optional, and you can always extract the value from it by calling value. Even the dereference operator is overloaded there for you to access the value. You can even query its value by converting it into a bool, or by invoking the has value function. Okay, so its existence is to be to make something to make it possible that something may not be there. So we don't want in our objects, whether it's your pointer, we don't want the null pointer. when it's a string, when we had strings in our example also, we don't want to have any special meaning to an empty string. We don't want any special meaning to a number 0 that it's not a valid number for you to use in your domain, even though you need it, because 0 signifies something erroneous. So we don't want any of that. The Std optional can just do that part. And it eliminates the need to check check before use of the domain objects, and your domain objects are pure also. They don't have to set aside a value for signaling error or incorrectness. So it's very desirable. So imagine that we write all of these functions, rewrite all of these functions with Std optional. So you get the file name. So we are back to the original code that when we started with C++11. If we write all of that code with Std optional, because that's the good place to start, you would get here, this is an optional. You can check if it's there. If not, then you are also returning an optional. You can return the nullop, which is a constant provided by Std. And that signifies the absence of the object or the value. Okay, so similarly, all these functions that we saw in the initial slides are now returning an Std optional. And these optionals, when they don't carry a value, you want to stop right there and just return null. Okay. As you see here, the information of which step failed is now lost. If you just return a null opt for reason number 1, 2, 3, 4, 5, 6, any of the calls, you might not, you don't really know which step really failed. C++23 is trying to address this. We'll come to this maybe later. So this is without pipes. This is our starting code when we come to C++17. The code we have there is just working with a T and a callable from C++11 that we have discussed so far. It won't work with optional because our functions don't take optional objects as passed parameters, which is what the existing C++11 operator that we have overloaded so far, that will end up doing. It will pass the object on the left into the callable. That's not what we want. We want to unwrap and pass the object. Okay, so we need to write something, a new overload. Okay, so we want to unwrap. So we have the same T and callable. You don't know what this T is, because now you see in the operator signature that T is the contained value, and we will take an Std optional of T and a callable, of course. So, and what is the return of this? Whatever the callable gives, we'll return that. Okay. As we know, all the callables are returning an optional. So we check this optional. If it's there, we use it. We invoke the callable with that, with the value contained. Okay, since this is an R value, you move it out and use its value. And so the value contained inside it is used, or else it's possible to have an optional which is an L value. We'll look at that shortly. So C++17 gives you invoke, and it gives you invoke result, and that's what we use in order to make the call happen. Again, with that magical implementation, our piped operations are back. Okay. And like I told you, there could be a const ref of the optional also, in which case we get a const ref of the optional and we don't move it out because it's const. You pass it on as a const to the function. Everything else is just the same. All right, so now it's possible to work with L values. I'm showing you how that is possible. So you have an optional of consumer received through these partial operations till you create the Kafka consumer. And then on the Kafka consumer, you want to call the further the operations after that, and you could do that here. And here, as you see, the optional itself is passed. So I could actually pipe it out, but that would create an R value of R value being passed from this statement to the connect. So I was just demonstrating the const, the L value part of it. So this would invoke the const ref implementation. Okay, so we are good with C++ 17 also. We surge ahead to C++ 20. Let's see what concept and ranges do for us. Now, of course, we have been calling the callable willy-nilly, just a callable. What is it really? We don't know. Is it the right object? We would love to constrain what we have. Okay. It could just, so this is the problem. This is the whole reason why concepts have come in, that they let you specify what really you expect from your objects, from your types. Okay. And let's state the intent in the operator. What we want is the operator. This is just like the previous slide. It's working on the T. Okay, so this is the overload with just the T being passed to the, the value being passed to the callable. Okay, this is just like before, and we just add a requires clause to this. Okay, so we say that it has to be an invocable type. Invocable callable with T has to be satisfied. If this is not the case, the user will get a very helpful error exactly stating that this invocation is the problem. The user won't have to drill down into 5 levels of depth of template errors, which would scroll 1.5 pages. And anyway, we started talking about concepts. So we use the concept invocable here in order to constrain what objects are allowed to be passed here. This operator is now callable only with the correct object. So far, of course, the code would not compile, but it would not give you helpful errors. Now it will also give you helpful errors. All right, so then we look at the operator. Does it at all interfere with STD ranges? I was very happily implementing the operator. And I just thought, why don't I implement with the operator in visible still to the code? I tried using some ranges code here. So with our operator, when we write some ranges, we have a vector of ints. I create a pipeline. This is the ranges pipeline where you say that you're transforming into squares. So I'm just doing squares of all the ints of all these ints. And then, so because it is lazy, I think you appreciate this, that this is lazy. You've just declared a pipeline. You have not traversed it. It's not eager. It's not already traversing, contrary to algorithms. Now you're traversing it here in the loop through the pipeline. And as you go, you are printing all the n and you get all the squares actually. I'm not showing you the output, but you can guess that this is working fine. Sorry. I'm sorry, it's not yet working fine because the first time I tried was without any consideration of handling for ranges. So we have definitely disrupted the ranges implementation and the overloading of operator specifically. It's ambiguous now. The compiler isn't able to pick between any T being passed to any invocable which can take it versus the ranges overload of the operator. That's the fun with polluting the global space. But with operators, we don't have a choice. So we need more constraints. Thankfully, C++ 20 also brought the concepts. Actually, they both were pretty much intertwined right from the beginning. So this is the concept from the previous page. And I'll bring in the requires clause. It's not only asking that this callable be invocable through T, but we also need that the T is not a range. When it's not a range, we let the other operator do its job. So in this way, we are mutually exclusive, existent in the same domain, in the same translation unit, in the same overload set, I should say, in the same overload set, but mutually exclusive. Because those operators actually rely on the T being ranges. All right, so now the ranges work. This is the main function, which I've never shown to you, but this is how I'm actually able to invoke Kafka. I can see that the creation is successful. This is using our overloaded operators that we have reviewed so far in this talk. And in the same breath, we have some code from ranges, which is able to transform its own vector. And they are coexisting, peaceful. And then we leap into the future. C++23 is bringing in Std Optional monadic operations. This is from the paper, which was this paper 0798. This is the example from that paper, but we have a very concrete example to work on. I would just highlight quickly what it is doing. Here again, like our example, all these functions are just giving you an optional. And once you see an optional is not there, you just stop your operations here. And that's how a lot of these chained operations, a lot of these operations are happening one after the other. In C++23, if you attended Cybrand's session 1 hour ago, or you didn't attend the other C++23 session happening right now, if you have not seen this before, this is just for you quickly. This is an optional which you get after calling the first function, but then you are able to say, and then add a bow tie, and then take the next operation, and then take the next operation, or you can transform into something else. We'll see the difference between these and then transform. But I already have an opinion looking at this much code. And yes, your guess is right. It's still too verbose. So for our case, if I use our function names, where we start with the environment variable and we reach all the way into a consumer subscribed to a channel, we have this code as our starting code from C++23. And I would love to have code which is using operators. If you saw that code so verbose, where you are saying to you're partly saying this to two people. One is the compiler, that this is a transform function, and this is a continuation function. Well, I don't think you need to tell this to the compiler. It knows how to work with both. And it is to the reader, yourself and your team members. That's where maybe it makes sense. But really, I've asked this, is and then mentioning, is it so important? Some people feel that it is important. Maybe I don't understand functional programming so much, but I would love to learn why it is so important. Because if you can see the pipe operation saying connect, what else do you think you can do? Again, it comes to that naming thing, which I was telling you. If you name your things correctly, your functions appropriately, you will not get confused. And just telling you that it's a transform which you yourself wrote, I guess, yeah, you won't know all the code, but I guess it's overkill. You don't have to say these things. And this is the reason why the world is loving these other programming languages, because they make it very easy to express things. But we have our controls and knobs in C++. Sorry, I had to add that for the love of the language. But anyway, so it's a big plus. Member functions do not add to the global namespace. It's a very big plus. Operator instead had to be global, right? Our operator. But a big minus that it is so verbose. Can't our pipes help? Yes, of course. Just quickly looking at what we have from the monadic interface. We have and then, which is to work with a function f, like you see here. It's going to take the result of the optional itself, the this, and pass its value to this function f, okay? And the function itself returns another optional of u, okay? This could be another optional of t itself. Maybe t is the same as u, but it gives you an optional. And that's what the return of this function itself is the optional of u. Whatever this f returns is what you would return. Okay, so you are an optional of t, you have that, and then has this as optional of t itself. It takes a function which takes the t and gives you an optional of u, and that's what you return back. It's just a little function utility like this, the kinds that we have been implementing today. Okay, so the return type of callable, what is it? Okay, yeah. So I was cheating all this while that the return types were all optional. I was returning null opt every time, but that's an assumption actually. It's not always the case that you would get a function which would return an optional. So the return type of this is an optional u. Okay. When you want to do sorry, so this is the operator just pasted from the previous slides. So this is just as is reproduced and reminding you that we are actually treating the return of this operator always as an option. I purposely did that to reach this point, but it's not right. It may not always be optional. Okay. So, but we want to now say that it is an optional. It returns an optional. And to be able to implement and then we need to be able to check that it is indeed a function which gives you an optional. If not, then it's an ill-formed function you would have read on that one line, which I included from the CPP reference. So here we can check that the return type is convertible into an optional t. But you know what? You don't know what the contained type of that returned optional is. The whole idea of this is that you don't know what callable is passed by the user. And so we have to introduce this new concept which checks that the return is an optional. Okay, so that's where we need to define a basic optional. I see some questions. I'll come to that in a minute. Excuse me. So we define a basic concept of optional. This is based on the Std optional itself, that it has to have a value type and it has to be convertible to bool so that we can check it, query it for the presence of a value. And its value type should be the same as the t that you, the t's value type, the value type inside the value type passed here would be the same as the value type inside the optional if you remove the CV. And it has to be constructible from null opt. So this is what creates our concept. So if we have the value of this object optional, so we are going to check an optional here. It is the same as its own contained value. So, the value type is also returning the same value. Sorry, it was a little. So maybe I can make it a little clear for you. The value type is what you should get from the dereferencing of that object. That's what this line is checking. Okay, I'm trying to dereference, and whatever the type is, if you remove the CV, it should be the same as its contained value type. So that also checks for the presence of this dereference operator in the object. Okay, so now we can now have our same operator as before, but of course we want to add on to this invocable constraint. We want to also add that the return type is a basic optional. So whatever is the return type, it follows all that interface. All right. And the const ref overload for this would be similar. just that you don't move out of the optional. And there we have all the and thens are now replaceable by the operator that we just implemented. I look at the questions now. Simon asks, does the version that describes the first argument being a range work with the previous example? The first argument was std string. Yes, very good point. In fact, I did hit this error. So this is one reason why you should also not use the t being passed. So if you have a range, yeah, this was working for me. I think the if you remember the error from the operator, the operator pipe overloaded for ranges takes more than one things, and I guess that's why it was not landing there. You are so right that our T may happen to be a container, and then it would just land in the ranges domain and not here. Yeah, I thought I solved that problem. So maybe this is still an open point. It's a good one to discuss. Thank you very much. And Andy has asked, is the range avoidance requires clause a type trait or something? It's a concept. The range requires is it can be a type trait or it can be a concept. Or you can define a concept right there in line without naming it. All right, so we'll go next. We look at transform. Transform again works on the optional, gives you a U. It takes your T, the value type T, and gives a U. This is now we are supposed to return this as an optional U now. So maybe it doesn't. So we need a new overload. Maybe the T doesn't work. The transform doesn't work. But the slight difference between these two functions is just in the return types. Of course, the operation they do maybe, but that's not up to us. We don't know what that is. So as you see, that transform also can be implemented with operator pipe. So here we have basic optional as the result of the callable. Oh, sorry, I'm sorry. There is a not there. So this is supposed to be returning something which is not an optional. So it is not an optional of any type. Okay, and we return an optional of the type that the callable returns. Okay, and so the implementation is pretty straightforward. We invoke the function and return the optional. Okay, and similarly, you can guess what the overload for constref looks like. So now we come to the parse Kafka config, and we don't have to implement it as something that returns an optional. It can just return the type itself, because now we have the operator implementing for transform also, and we have this C++23 code, but it is still working in C++20. Despite we starting from C++23, which is a plus that you can work on something which is you can already work in that domain. All right, so there is an or else monadic interface. Also, we can hack our pipe to doing this, but a pipe can mean just one thing, something that consumes your value. We have already used it for two different kind of things, and this one is like a value or. So you take a function which takes no parameter, and you use it for implementing the case that the optional is empty. So if the optional is empty, you take the value from this callable. I'm not going to cover this. I'm running out of time. So if you want, you can still implement it this way. And here there's no distinction in writing the operation on the same line or a different line, but I've written it in the same line just for you to know that that one is the or else overload. Okay, I think this is loss of meaning, and you should not use this for or else. Don't hack your way into things. All right, So we have other wrapping types, std expected, which is supposed to carry the error along with the return object. This is the Rust equivalent of result. And you could have futures, which is also pretty similar. They are just wrapped entities. But future has a function called as then and not and then. Anyway, you would have to implement something specific, a specific operator for each of these types. I have not tried async yet with chaining operations, but that's where we are. In conclusion, I would just say you get functional, make pure composable functions, and use value semantics. It may not fit every case, like asynchrony or branching. So I was thinking of implementing a T of the pipe, but not today. We can talk about it. Reach me out. And multiple returns from a function, all that I'm not, if you have that case, maybe you don't want this. You don't want to use this. Okay, and there are some disadvantages. I want to just mention these before we leave. The operations could be too granular. They could hit performance, even compile times very heavily. There's a recurring work for every new type that you want to support. You want to come back and add a new overload. It make the operator being global may conflict with some other operator. Maybe somebody has a type and suddenly, just because it implements the callable, it just starts, our operator starts getting used. And due to the long chain, human perception, the understanding of the code goes down. All right. So keep making effective, efficient, and elegant solutions. Thank you very much for joining me today. I think there are some questions. I'll see you in the session chat. Thank you very much, everyone.